what we are going to do is sort of pick it up where we left about I think 10 days back. That is, we are going to discuss the topology of these systems, namely topological insulators. But for that, we'll first try to start from the 2D spin-Weyl systems. This is something that we covered in the last class, but anyway, let's just start from here. So the first thing that we want to do is to sort of understand that a basis for classification of these 2D spin-Weyl systems in terms of topological numbers. Okay. So the way to do this is the following. So first, let's consider a two-dimensional time reversal invariant system. Okay, and let us also consider a set of two bands which are Kramer pairs. That is, if one of the bands have upspin, the other one has downspin. That is, the bands are time reverse counterparts of each other. We know that time reversal symmetry for spin-off fermions do not allow up and down spins to be totally degenerate, to form totally degenerate bands. They must be, well, to form, they cannot be the same band. They have to be, they have to form a pair, and this pair is known as the Kramer's pair. So essentially,
मैंने सुना उसको अभी तक नहीं मिला, अभी तक तो नहीं मिला ऐसा। उसको कैसे नहीं मिला यार? मैं वही सोच रहा था, मीटर किसी बताएं, बोले मेरे भाई को तो बहुत जन को नहीं मिला, तो बहुत जन को मिला ना किसको? अच्छा,
okay, so
भी नहीं है बस उनको पता मेल लगा तो कॉलेज में कि आप लोग वैक्सीन ले लो, उसके बाद में बुला देंगे। फिर उनको मेल डाला कि
हेलो प्लीज म्यूट। Okay, it's muted.
Great, thanks. So, okay, so for such bands, what happens is that time reversal symmetry demands that the energy of the band, of the upspin band at K is same as energy of the downspin band, but at minus K. This is because all physical quantities should remain invariant under time reversal symmetry because it's a TRS invariant system. However, if these bands ever have to cross, and they can only cross at special momentum, because if E up of K naught is equal to E down of K naught for any momentum K naught, then it also has to equal to E up of minus K naught. Okay, that's from the first relation here, and that's a consequence of time reversal symmetry, which essentially means that for a general band with general dispersion E of K naught, the generic points where these things can cross is K naught equal to 0 or Q by 2, because 2 K naught will always be 0. Of course, in a standard system, this would mean K naught equal to 0, but here in a lattice system, it also means that K naught could be a reciprocal lattice vector, namely Q. So could be 0 or Q by 2. Okay. So as a result, what happens is that these are called time reversal invariant momentum points, or TRIM, and this K naught essentially, so these are points where K is mapped to itself by time reversal invariance, and these are the TRIM points. Okay. So they can. So the first statement is that these bands can only cross at this TRIM or TRIM points. Now let us now take a band and have its wave function, which is, let's say, UK sigma. Sigma can be up or down, and correspondingly we can construct a charm, so a Berry potential, which we discussed in previous classes, which is obtained by superposition of, well, it's just U star del K of U. That's the Berry potential, and if you take the integral of this over some reasonable momentum contour, you get a number which is the Chern number corresponding to the band. This is indeed what we have discussed before. Okay, so for corresponding to each band, I can have a Chern number. So if the band is completely topologically trivial, this Chern number would be 0. If it is topologically non-trivial, this could be some number. Now let us look at what happens at the crossing. Now when the bands cross, they can so before and after crossings, their Chern number can change. This is something that Rahul Roy showed, and the way to understand it is that this crossing point is a singularity as far as the bands are concerned, and because it passes through a singularity, its charge number can change. Okay. Remember that these crossings, if I go sufficiently near it, are like Dirac points, and Dirac points we saw are like vortices in momentum space, which are like singularities, and when the band circles such a vortex, okay, it essentially means that so for example, when you are computing this integral of dk a, if you are circling one such vortex, it essentially means that your charge number can change. But how do they change? What Rahul and others showed is that they can change by just an integer, and this integer could be 1 and 2. So now imagine summing over the total charge number of all bands, and the rule is that if you sum over certain bands, you should not include the time universal counterpart of this in the sum, because otherwise everything is 0. Because if the charge number of a band is, let's say, n, its time universe counterpart has a charge number of -1. Okay. So charge number is invariant, goes up to minus of itself under a time universal symmetry. Now the point is that suppose we do this, what happens? You see, if there is a crossing at one of this k0, okay, then within the Brillouin zone there is also a similar crossing at -k0. That's guaranteed by time universal symmetry. And it is also guaranteed by time universal symmetry if a Kramer's pair cross, and if one of the bands pick up a delta n at one of the crossings, it's going to pick up the same delta n at the other crossing also. Therefore, the total change in charge number of any bands can only occur modulo 2. It can be 2, 4, 6, 8, 10, etc. because it can be integer at each crossing, and there are at least 2 such crossings at k0 and this time universe invariant point. And therefore, the sum that we obtain by computing this sum over charge number is its parity, that is whether it's odd or even, cannot change upon band crossing. In fact, you can do any kind of crossing between any kinds of bands, and you can show that this number mod 2 is an invariant for the lattice for a particular system. Okay, it doesn't change upon band crossing. And then what Rahul and his fellow collaborators showed is that if you have, let's say, 0 such crossing, then clearly you have a trivial insulator. And therefore, by extension, anything which is 2, 4, 6, 8, etc. are also trivial insulators. However, if you have odd number of this, there is at least 1 crossing, and these are topologically non-trivial insulators. Now, the point is that what we saw in the previous classes is that corresponding to a spin Hall insulator, there is a pair of phase states which moves, which have opposite chiral. And we reason that if we have these states and we cannot really have interaction between them unless time universal symmetry is broken, because a potential cannot scatter between an upspin state to a downspin state unless it is allowed to flip spins, and those kind of potentials are magnetic potentials which break time universal symmetry. However, if that doesn't happen, then this pair forms a pair of gapless modes. However, if there are 2 such pairs, that is 4 states in total, the up bands can interact between themselves and the down bands can interact between themselves, and they can gap out each other. Okay, and therefore those are not topologically protected. And that is another way to understand why this I equal to odd 1, 3, 5, etc. are topologically non-trivial states. Okay. Another way to understand this is that if you have such crossings, if there are 2 such crossings in your Brillouin zone, okay, then what happens is that, I'm just considering 2 crossings at k01 and k02. I'm not counting the one which will also be there at -k0 and -k0. 2. So if these are there, and then I can tweak essentially band parameters. I can bring those two crossings close to each other by tweaking band parameters. I can change their positions, and they may annihilate each other, which means that under perturbations, this is not topologically protected. However, if there are odd number of them, at least one will always remain. Okay, and therefore these are different from trivial insulators. You cannot mold them or modify them to form trivial insulators. Okay, so the point is, the bottom line of all this is that if this topological invariant is odd or 1, not 2, then you have a topologically non-trivial state, okay, or an insulator. And the upshot of this, in case of 2 dimension, is that you have a non-zero spin quantum Hall number and a pair of H states at the bottom, at the edge. So, is this part clear? Any questions regarding this? Anything which is unclear or any other? Okay, if not, then we'll see how to extend this classification in 3 dimension, which is relevant for topological insulators. Now, in 3 dimension, what happens is that you cannot really define bands over the entire, you cannot really define Chern number over the entire volume or the entire Brillouin zone, because Chern number can only be defined in 2-dimensional space or momentum space for that matter. Okay, so what people do is the following. So first thing is that you choose 3 planes which characterizes your volume of this 3D systems, and the way to choose these planes is such that they are time inverse counterpart of themselves. Okay, so for example, if I take a plane which is kx equal to 0, it means that it has all points which are 0, ky, kz. And under a time reversal symmetry, any point is mapped onto 0, minus y, minus kz, which means that any point on the plane gets mapped onto another point on the plane under time reversal. Okay, so all momenta in the plane stays inside that plane under time reversal symmetry. Okay, such planes are called time reversal invariant planes. And the 3 obvious choices are kx, ky, and kz equal to 0. Those are the things that we are doing. And then, corresponding to each, I can define 3 invariants, just as I did before for the 2D plane. So these gives me 3 numbers, mu1, mu2, and mu3. And these are the invariants for this 2D systems. Now the question is, if let's say I have this mu1, mu2, mu3 to be 1, 0, 0. Do I have a 3D topological insulator? And the answer is no. Because you see, then there is no difference between a topological insulator and a stacking of spin-Hall systems which are stacked over one another, in succession. Okay, that will also give me these 3. This can give me, mu1 to be 1 and mu2 and mu3 to be 0. It's perfectly possible to stack 2-dimensional systems on top of each other to form a 3D system which is going to behave in such a way that they are going to have one integer non-zero and the other one 0, and so on and so forth. Okay, but the point is, these 3 integers give you a hint about what the topology can be. However, they do not classify, they are not enough for classifying a 3D topological entity. What one needs is a 4th invariant, which is nu naught. Okay. So what is this nu naught and how do we understand this? So the nu naught essentially shows if there is some non-trivial topology truly in 3 dimensions, okay, and which is not restricted to a plane. So how do we figure that out? We figure that out by considering a solid, let's say a cubic solid, which is for which we'll consider a solid which is centrosymmetric, which means that for this solid, parity is a good quantum number at special momenta, such as k equal to 0 or q, which are crystal momenta. Now, what does that mean? It means that a parity acting on psi, any wave function at k equal to 0 or q, essentially leaves it invariant. Okay, so that's what it means, up to a +1 or a -1 sign, and that's what it means. So the wave function at that key point is an eigenstate of the parity operator. That's what it means. Okay. Now, how many such points are there? Well, in a 3D system where you have a cubic lattice, you have 2 to the power d such points, where d is 3 here, so 8 particular moment. So now imagine computing the parity of a band at k equal to 0 and at k equal to one of these q's, okay, which is given by something like, let's say pi by a, pi by a, but pi by a, pi by a, pi by a. So that's pi pi pi. That's one of the possible q's of a 3D cubic solid. Okay. Now, okay, so let's do that. So the point is that, so now let's look at this. So imagine that at 0, the parity of a band is 1. So unless there is a crossing of some sort, or unless there is a band inversion in between, okay, this thing will remain to be 1 at Q. But if there is a band inversion, and if the other band has a parity which is different, which is typically the case for these Kramer pairs, then of course the product of these two parities, P1 at k equal to 0 and P1 at k equal to -1, Q, is odd. Okay? Otherwise it's even. So now you can define a topological index, okay, something like this, where I can define this delta J, which is this quantity 1 minus. So I sum over all such n's, okay, that is sum over all such qn's. This n corresponds to the different reciprocal lattice vector, okay, and I take the product of P out here, okay, at 0, and then out here at Q, okay. So this means that, so for example, for this example, for band 1, P1 is 1, P and at k equal to 0, and P1 is -1 at k equal to -1. So this product is -1. Okay. So this delta J, if I consider both bands at this crossing, this delta J could be either 0 or 4. Okay, because if it is -2 here, it's also going to be minus. So if this product is -1 for the first band, 1, it's also going to be -1 for the second band, which is 2. And therefore, this sum divided by 4 is going to give you 1. If it is +1 for both, if there is no avoided level crossing, this sum is going to be 0. So now I can think of an invariant mu naught, which is mod 2. This quantity mod 2, it's either 0 or 1. Okay, 0 again essentially means that there are no or an even number of band inversions, which leads to trivial topology. And mu naught equal to 0 essentially gives you what is called as a strong topological insulator. Okay, these are the topological insulators where the surface has individual Dirac modes, a single one or an odd number of Dirac modes, and those are the insulators that we are going to talk about. Okay. So, any questions regarding this? Is this classification scheme clear? Any questions? Anything which is unclear? Okay, if not, let me get into the details of these topological insulators. So what we have seen is this, and then from here. So I've covered this verified stuff and the topology. Okay, so essentially there is this fourth invariant which I explained. Okay, and I'm going to only consider the strong topological insulators. Okay, and these strong topological insulators, it is seen is what is seen is that just as the two-dimensional spin quantum Hall effect has chiral edge modes, they have odd number of chiral theory at the edge, and these are typical Dirac points. Okay, so we have already discussed this a bit, so I'm not going to spend more time on this. But let me now getting to the point that if you do have these Dirac cones on the surface, what are the properties of these Dirac cones, and what physics can we get out of this? Okay, so that's the essence of the rest of the talk. So the first thing about these Dirac cones is just like the Dirac properties. Okay, unlike the Dirac cones in graphene that you see, there are two differences. One of them is that this Dirac theory pertains to the spin of the electron and not some pseudo spin. So this two-component field psi k that you see here, they correspond to spin up and spin down, and not some pseudo spin up and pseudo spin down. Okay, so this has ramification for magnetic properties of the system, which I am going to come to. But this is the first thing that one needs to know about topological insulator Dirac cones. Okay, so the up down here are really the real spin up and spin down. That's the first part. The second thing is that there are two possible forms of this Hamiltonian. One is the sigma dot k, and the other one is sigma cross k dot z hat, where z is the direction perpendicular to the plane, the surface at which these Dirac cones are. And typically it is seen by experiments, and I'm going to say what experiment is that in just a moment. That this is the so this essentially happens to be the particular form that is realized on the surface of the topological insulators. There is no particular reason for this. This is a consequence of the band properties. But the point is that this is typically seen in experimental situations. Now, if I diagonalize this matrix, which is something like sigma x ky minus sigma y kx, which is very easily done, I again have the same energy as that of the Dirac electrons in graphene. That doesn't change. However, the wave function now changes, because instead of a 1 I e to the power I theta, you have a instead of a 1 e to the power I theta, which was same for the graphene electrons, here you have a minus I factor sitting in here. Okay, and that's because you now have sigma y coupling to kx and so on. Theta again is the angle at which these electrons move. But now imagine that an electron moves along x, so that ky is equal to 0. Okay, so this means that if I just put theta equal to 0 in this, because theta is tan inverse of ky over kx, then what I find is this is 1 minus I, which is an eigenstate of sigma y. Okay, so the spin points along minus y, or is it minus? Yeah, it's minus y. The spin points along minus y if you are moving along x. Okay, and so on. So the point is that you can do this with other things. For example, if it is just moving along ky, okay, if it just moves along y in momentum space, so then theta is pi by 2, and in this case you see that it's 1 1, which is an eigenstate of sigma x. Okay. So here it seems that the helicity property of these Dirac electrons shows that its spin, and remember spin not pseudo spin, points perpendicular to the direction of its motion, and that is a consequence of having this sigma cross k dot z hat. Okay, so that's the first difference. So the spin orientation of this Dirac, so if you have a Fermi surface around this Dirac point, the spin orientation of the electrons around this Fermi surface would be like this, because you see at each point on this Fermi surface, the velocity of the electron is sort of like moving perpendicular to the tangent of the surface. So for example, at this point it's moving towards x, etc., and therefore the spin is perpendicular. The green arrows are the direction of spins. Okay. Also, because you are dealing with the real spin, if you apply a Zeeman field which is perpendicular to the surface, okay, then it opens up a gap. Okay, which means that because it gives a sigma z component, so the Hamiltonian now becomes this plus B naught times sigma z, and if you diagonalize that 2x2 matrix, you see that there is an energy gap which opens up, and that gives you massive Dirac particles. So you can control the gap of these Dirac electrons by simply putting a magnetic field, okay, perpendicular to the surface. So these properties are not too different from that of a graphene. Indeed, in graphene, if you, instead of a magnetic field, if you could have put in something similar to a strain, you could have done this. But the point is that magnetic fields are much more easily manageable in laboratories. What is really interesting here is the application of a constant magnetic field parallel to the surface. So if I have a TI surface like this, a topological insulator surface like this, and if I put a magnetic field which is along Y, then something interesting happens. And to see what happens, let me get back to one of the later slides, which is supplementary slide out here. So imagine that I have, so this is my Hamiltonian at a given K, which is sigma x ky minus sigma y kx. And now I apply a field along Y, which means that gives me a Zeeman term, which is G mu B times B in the Y direction. So I can combine that term with this Hamiltonian, because that also has a sigma Y, because it couples to Sy. Okay, then this means that all I have is a shift to my, okay, so I have here applied a magnetic field along X actually, not along Y, sorry. So what it means is that my Ky gets shifted to alpha times B. So I'm applying a field along X, sorry, this would be X actually. So I apply a magnetic field along X, which means that it couples to sigma X linearly, which means that this Zeeman term essentially acts as a shift in Ky. Okay. But then you see my Hamiltonian really doesn't change. The reason is that I can now simply shift my Ky origin. Okay, that's just a constant shift of momentum, and I can reduce this Hamiltonian to the form before, which essentially means that all my energy dispersion, etc., would be, everything would be same. Okay. Another way of understanding this is that this is equivalent to applying a gauge potential, and as long as that to the electrons, because this gauge just shifts Ky to Ky minus Ay. So this quantity alpha B now acts as a constant gauge potential, and we know that a constant gauge potential, but if the magnetic field, that is, if the magnetic field is a constant, this acts as a constant gauge potential, and we know that a constant gauge potential cannot really change physics, because it doesn't correspond to any realistic electric or magnetic field. Okay, so this means that putting a constant magnetic field parallel to the surface does not do anything to the Dirac electrons. Okay, of course it doesn't do anything orbital, because if you put a magnetic field parallel to the surface, you can just choose to describe it using a gauge where you just have Az, and it doesn't couple either to Kx or Ky, so no effect there. In a general 2D system, if you apply a field parallel to the system, there is no orbital effect. That's simple classical mechanics. That's really simple thing. Okay, so however, in standard Schrodinger electron, you still have a Zeeman effect. Okay, here you don't. And I'm going to come back to the reason for this in a moment. But notice another thing which is going to be important for us for later discussion, is that suppose now this magnetic field becomes a function of, this would be again Ax and this would be Ay equal to 0. So if this magnetic field now becomes a function of Y, then I have a non-zero curl, and therefore I'll have a effective magnetic field which depends on the gradient of the applied field in the problem. Okay. Now this, I'm calling it a fictitious magnetic field. However, it is not. You see, what happens is that the electrons essentially, the graphene, so the topological insulator, these Dirac electrons, they perceive this gradient as a fictitious magnetic field, and they do undergo for example, in a semi-classical way of speaking, a cyclotron motion corresponding to this gradient. Okay, so this feature is completely different from standard Schrodinger electrons. Standard Schrodinger electrons, you are going to see cyclotron motion or Zeeman effect depending on the magnetic field. Here it depends on the gradient of the magnetic field. Okay, so any questions regarding this? Anything which is unclear?
So I don't understand the dependence of the gradient. Can you explain that? I mean, physically, what does it mean? Here, obviously, the mathematics is clear.
I'm sorry, Kishore, can you speak up a bit?
Hello. So what I'm saying is, I don't understand how. I mean, this dependence on the gradient of the magnetic field. I mean, the mathematics is clear, but physically, what is happening?
Yeah. So the point is that if this B is a constant, then you realize that this alpha B term is like just like a constant gauge potential. That you agree, right?
Yeah.
So this means that it cannot have any effect on the electron because a constant gauge doesn't really do anything to the motion of an electron. You agree to that, right?
Yeah, I agree. Yeah.
Okay. Now imagine that you apply a field which depends on position, so that it is a non-zero curl. Okay. So then, of course, because this is like a gauge potential, this B of, so if this B depends on Y, then I have effectively, it's like applying a gauge potential which is a finite curl.
Okay.
So the electron which sees this magnetic field as a gauge potential, essentially going to see its effect as that of a fictitious magnetic field. And I am calling it fictitious because you haven't manufactured that magnetic field in your laboratory. Magnetic field is something that is perceived by the electrons and it depends on the gradient of the actual magnetic field that you put in.
Okay.
You see the point? I mean, yeah, so it's important to make that distinction actually.
Yeah, so the important point is that this is different from normal Schrodinger physics.
Different from the normal Schrodinger part.
Okay, sir.
Okay, because so I'm coming to what the difference is from the normal Schrodinger part. Okay, so let me just go back to the slide where I was before coming to this, and let me tell you what the distinction is. Okay. Yeah, here. So you see here is a, so in a conventional material, if I apply a magnetic, in a conventional two-dimensional material, if I apply a magnetic field parallel to the surface, I am not going to have any orbital motion in the in-plane magnetic field. Why not? Because of course, that's because I can always say that this magnetic field is described by the Z component of a vector potential and nothing couples to Kx or Ky. So no orbital motion. Same is true for topological insulators. Okay. But in the conventional materials, remember that when you have said that this plane is your XY plane, you haven't fixed your Zeeman, you haven't fixed the axis in the spin space. So you can still say that my magnetic field couples to some Zeeman term, which is like a sigma z dz. Okay? Because there is no connection between the axis in the real space and the axis in the spin space for a conventional material. There is no spin orbit coupling. Okay? So essentially, you can still say, well, I'm going to choose Z to, in spin space, I'm going to choose Z to be the axis, which is the direction of magnetic field. So you just put a sigma Z times B, and that gives you the Zeeman. However, when you write the Hamiltonian of a Dirac electron on the surface of a topological insulator, and you say that my Hamiltonian is sigma dot k or sigma cross k dot z, whatever, you have already put in your choice of axis not only on the real space but also on the spin space, because you are associating a sigma matrix, a Pauli matrix, with the momentum. That's what spin orbit coupling does for you. Okay? It just couples L with S, which means it couples the axis choice between the real space and the spin space. Okay? Now, once you apply the magnetic field, you cannot say that the direction of the magnetic field is the direction of your spin quantization axis anymore. You have already chosen that direction because of this spin orbit coupling, and therefore the effect of the magnetic field is completely different. Okay? So it's a fundamental consequence of having a strong spin orbit coupling term. Okay, so the point to make is that applying a constant magnetic field parallel to the plane has no effect on the electrons on the surface of a topological insulator. However, it does so through Zeeman effect for conventional Schrodinger electrons. Is that part clear?
Yes, sir.
Okay, great. So now let me move on and discuss some. Let me move on and discuss some experiments that one can discuss. So these topological insulators was first suggested by band theory calculations, but later they were verified by experiments, and there are several experiments which came out at that point, and all of them, well, almost all of them, are RPS experiments, which means that it's an angle resolved photoemission spectroscopy, where you direct a photon of known momentum and energy to the surface. It kicks out an electron from the surface, and you sort of look at that electron and find out its momentum and energy. And in the case of a 2D surface, the conservation of energy and momentum essentially allows you to map the position of that electron on the Fermi surface. Okay. Because you know both its energy and its momentum, and then therefore you can draw the borders where the scattering produces electrons, and that way construct a Fermi surface in the 2D plane. Okay, so this is, for example, the picture of a Dirac cone which goes from gamma to m and here from gamma to k, and this is essentially. So this is another picture. So these pictures are reconstructed from RPS data by reconstructing the position of the kicked out electron from the Fermi surface bit by bit. Okay. So this clearly shows these bands, okay, Dirac-like bands for these topological insulators. Okay. So, but the clinching argument for this theory came from what is called a spin resolved angle photoemission spectroscopy, which was done in Zahid Hassan's group in Princeton. And what they did was that they did photoemission, the standard photoemission, and so that they know where the momentum of these electrons are on the Fermi surface. But what they did was also to measure the spin of these electrons with some precision, and they could show that no matter where they picked up electrons from the Fermi surface, the spins always point perpendicular to the direction of motion, which essentially pointed towards that sigma cross k dot z type of Hamiltonian, because the helicity indicates that spin is perpendicular to the motion. And the second one is to say that essentially in each point on this Fermi surface, the electron has a particular helicity, and that very strongly pointed to Dirac theory describing these electrons on the surface of a topological insulator. So this spin resolved RPS was a clinching argument for Dirac physics on the surface of a topological insulator. Okay, so there is another experiment which came up and which also showed this. This was done in Hari Manoharan's group in Stanford in around 2009. So what they did was to have an STM on a surface, and this STM essentially had a Dirac. This surface had a Dirac band like this. Okay, and they could pick up. So they could project electrons from STM on the surface, STM tip on the surface, and they could do this for these points. Okay, this is essentially where the contribution came just from pushing electrons on the surface on these Dirac bands. And you see that normally they have very strong scattering, okay? And this scattering came from the fact that there are some inhomogeneities like states, etc., on the surface of these Dirac electrons, which essentially scattered the injected electrons from K to minus K. Okay? However, these kind of states who scatter electrons from K to minus K, provided it was lying on this Dirac band. And the reason is that, remember that corresponding to every K on the Dirac band, there is a spin direction. And therefore, for this state to scatter electrons from K to minus K, it must also reverse its spin. Remember this Klein paradox seen in graphene? It's exactly a similar phenomenon. So there was no scattering between electrons. So there was total absence of backscattering. And this backscattering was what was giving this, this rough looking image in Scm spectra, and there is a theory for it. So when the backscattering disappears, the Scm spectra becomes very smooth, and they found this precisely, at the location of these Dirac bands, which also showed that this kind of stuff shows Klein tunneling, and therefore this must be Dirac-like objects. Okay. So this was Scm data. So now for the rest of it, I'm going to talk about several properties of transport on the topological insulator surface and show how these are different from standard conventional Schrodinger electrons. Okay. So any questions till now? Which is left out, anything that you didn't was not very clear, I could explain again or anything like that. No.
Hello.
Please.
So the effect of magnetic field that you talked about, that is only for the two-dimensional insulators, right?
Yeah. Yes.
So I mean, do we have something non-trivial for three-dimensional topological insulators as well? Or
the point is that the bulk is usually insulated, so the effect doesn't show up in transport and other things. But the statement that I made was explicitly for two dimension. It was for the Dirac electrons on the surface of a topological insulator. This statement was not for the bulk electrons which had topological, which is in the bulk. Okay.
Okay. Okay. All right.
Okay. Any other questions? Okay, so if not, let me just quickly go through these junctions of topological insulators. So the first thing, so there after this thing came up, people were trying to look for several properties of this topological insulator. So I'm going to go through them one by one, at least some of them. So the first thing is that what they found is that if you put in a magnetic material on top of this topological insulator surface, then you induce a magnetization. Okay. So now what people did is to consider a geometry where you have this topological insulator surface and you put in two magnets, ferromagnets on top, side by side. And the first one has a magnetization which is along Z, perpendicular to the surface. So it gaps out, so it basically gaps out the Dirac electrons in this region. And in the second case, there was, of course, this magnetization, which is at an angle given by theta and phi. And they wanted to find out that how a current moves from one region to another. So what they do is that they pass a current and measure the voltage. Okay. So the most interesting thing that they found out is that so the thing is different if the junction is perfect and if it is strongly backscattering. That is, if there is a big barrier potential in the junction between these two F1 and F2, then the feature is different compared to what you have for a perfect junction. For the perfect junction, there is this interesting thing that as you vary the azimuthal direction of this magnetization, okay, it seems that you have a variation of this magnetoresistance. So what they measure is conductance or resistance in the presence of this magnetization, and they call it magnetoresistance, of course. So what you find is that there is a phi dependence or an azimuthal angle dependence. Now this is non-standard, and the reason why it is non-standard is that normally what would happen is that these magnetic substance would induce a Zeeman-like field, and this Zeeman-like field essentially, if it has any effect, it will depend on the relative orientation of these two magnetic materials, and that relative orientation is always going to depend only on theta. Okay, because if you have two of these magnets, one along up and the other pointing this way, it's really this angle, which is theta, which essentially is going to control the magnetization. Usually, it doesn't depend on phi. So essentially, it turns out that here it depends on phi. And again, I'm not going to discuss this in details. You can look at this paper by Yokohama et al. This is in the archive in 2009. It later became a PRL. But the point is that this has to do with the spin orbit coupling. Okay, the fact that your spin quantization axis has already been determined for this Dirac electrons. Also, it turns out that the magnetoresistance could be very, very large. Okay, and much larger than standard materials, which was good, which was one of the things that they pointed out in this paper. So the bottom line is that we could induce magnetization on Dirac electrons, on the surface of a topological insulator, and that gives you a few unconventional features for magnetization. I'm going to come back to these unconventional features in a few slides, but let me just go over. The other interesting thing, which was first pointed out by Charlie Kane and Liang Fu, is that the surface of a strong topological insulator, which hosts a single Dirac cone, for example, they have one state per momentum. Okay, and this is something that I would like to point out, and this is one of the fundamental things which is different for a topological insulator compared to a standard, conventional Schrodinger electron. So in a Schrodinger electron, you think of a given momentum. It has an energy h squared k squared by 2m, but this state can be occupied by both an up electron and a down electron. So there are two states per momenta corresponding to two spin directions of the electron. However, in topological insulators corresponding to a given k, we know that there is only one direction of spin. That's the essence of helicity for you. So you have one state per momenta and not two states per momenta. Okay. So for a single Dirac cone, you have just one state per momenta, and this is a signature of fractionalization, because your number of states over the entire Brillouin zone for just these bands is half the standard number of states. Okay. Now, so Fu and Ken pointed that out, and then they showed that if they bring a superconductor which is close, SOF superconductor in close proximity to a part of this superconductor, to a part of this topological insulator here, see this S, then this is equivalent, and this is a complicated calculation which I am not going to get into. What they found out is that the effective theory for such a system mimics a P plus IP Hamiltonian. It's a time universal broken topological superconductor, time universal broken superconductor, okay, where there is a pairing amplitude, which is delta e to the power I theta k, where theta k again is tan inverse of the momentum ky over kx. Okay, but the point is that if you have such a pairing P plus IP, and I'm going to cover this in the next lecture, you are always going to have chiral edge modes, because by this you have broken time universal symmetry. And the way to see this is that if you take a time universal operation on this, you see that theta k is going to change to minus of theta k because of this I factor here, because time universal comes with a complex conjugation, and therefore your system is not the same anymore. Okay, so the point is that this breaks time reversal, and as a result, what happens is that you have chiral edge modes, okay, flowing at the edge of the sum. And then they pointed out that if you bring that in connection with a ferromagnet, where there is one momentum per spin also, this is a ferromagnetic metal, okay, and this is a superconductor, and so below it there is magnetization induced here and superconductivity induced here. You are going to find that there are Majorana modes which are chiral. Okay, so this was something that Linder and Al pointed out. So now using this, and this is the thing that I wanted to point out, they devised, this Bineker came up with a really cute experiment. So as I said, depending on this, so they made a junction of this superconductor and a ferromagnet, and depending on the spin direction of this ferromagnet, chirality of these edge modes, okay, can change. So, for example, if the ferromagnet points towards up, the edge modes move towards one direction, and if the ferromagnet points towards down, it moves in the opposite direction. So then Bineker came out with this idea that imagine this junction where you had a superconductor out here, everything is on the surface of a topological insulator. So you have a superconductor out here, and then a downspin ferromagnet on this side and the upspin ferromagnet on this side. So that you have a circulating Majorana modes which moves in this direction. In the right, in this junction, it moves along this, and also in this junction, it moves along this. Okay. So now imagine putting a voltage across this and pumping one single electron in this region. Okay. Now here the electron splits into two Majorana because, of course, in this region the electrons are not eigenstate, but the Majorana fermions are, and the electron splits up into two Majoranas B and C. So their wave functions are given by gamma B and gamma C, and the electron is a linear combination of this gamma B and gamma C. Okay. So an electron creation operator is given by gamma B plus I gamma C, whereas an electron destruction operator is given by gamma B minus I gamma C. Gamma B and gamma C are real valued fields describing Majorana fermions. Okay, I'm going to cover this Majorana fermions in the next lecture in complete details, but for now just accept this. Well, okay, so we're going to come back to this later. But now these two then travel in opposite direction, okay, gamma B and gamma C, and they reunite here. Okay. Now, while doing this, normally it splits. So if there is an electron, it will come and unite as another electron. However, if there is a vortex in this superconductor, this entire thing corresponds to picking up a 2 pi phase because it's analogous to fermions circling a vortex, and they always pick up a 2 pi phase. Okay. So if there is a single vortex and you started with a gamma B plus I gamma C, you are going to pick up a gamma B minus I gamma C. So you start with an electron which is given by this gamma B plus I gamma C, and you end up with something called gamma B minus I gamma C, which is like an electron destruction operator, which means that you have created a hole. A destruction of an electron is analogous to creating a hole, and the remaining 2e charge has gone inside this superconductor. Okay, so this is a spontaneous conversion through this Majorana fermions and vortices from electrons to holes, and therefore, if you measure the current through this, every time a 2e charge goes in out here, you have a conductance of 2e over h bar. Therefore, you find out that the number of vortices can be measured, or the parity, whether it's even or odd, can be measured by just doing this experiment. Okay. So the tunneling conductance, it turns out, as shown by Bineker, oscillates with the number of vortices if they are odd, or even. Okay. So essentially, this kind of stuff, leads to breaking an electron into Majorana modes, and reuniting them. But in the process, if there is a vortex, you pick up an extra phase because you are circling around the vortex. And therefore, this leads to a consequence, a measurable consequence that your conductance changes. Okay, so these kind of platforms, these Dirac fermions, allows you to do interferometry with Majorana fermions. Superconductivity and these Dirac fermions together with magnets hooks up this kind of situations where you can do interferometry with Majorana fermions. Okay, so this is something that has been put forth. Of course, it's too complicated for experiments, hasn't been done yet, but this is a really cute theoretical idea. Okay. So, any questions regarding this?
So, what are the experimental difficulties when performing this?
What are the experimental difficulties?
Yeah.
Oh, the thing is that these kind of junctions, they are notoriously difficult to make because all of these theories essentially consider ballistic junctions, and real systems really have some disorder, and nobody knows how to calculate the effect of disorder in this kind of junction, so it's not very clear. Also, disorder is most likely going to spoil this effect because you are not going to have a coherent motion of this Majorana modes over a long distance, which will encircle a superconductor. So, very clean surfaces of topological insulators has not been made. So that's the main difficulty. Okay.
Okay, sir. Yeah.
Okay. Any other questions? Anything which is unclear? Okay then. So let me now talk about two more. So I'm going to talk about two more things which are again associated with transporting these junctions. And these essentially shows that you can have very different effect for magnetization on top of our topological insulator. So here consider this geometry where you have a topological insulator surface, but in region 2 you deposit some ferromagnetic materials which has magnetization pointing parallel to the plane. Okay. As we have seen before, that in the center of this region where this magnetization is constant, of course there is no effect because a constant magnetization, which is analogous to a constant magnetic field in the z direction, they do not really matter much. Okay, so because that's like a constant gauge. So I'm going to sort of take this example. Okay, so now let me first show you the quantum mechanics of this. So if I put in a magnetization like this, just consider the left geometry, forget about this right geometry for now. Okay, then what I have is the following. You see that I have magnetization proportional to sigma y out here. This is the y direction. Okay, this is the induced term because of this magnetic material. Okay, some ferromagnet with magnetization along y, and this is there. This is a strength J, and it is there from a region x equal to 0 to x equal to d, okay, of length d out here. So the proximity in these terms with J proportional to m naught is given in region 2. Okay. Now you see that this is similar to the vector potential for the electrons out here. But right at the edge where this thing goes from m0 to 0, because you cross over from 2 to either 1 or 3, they essentially leads to a fictitious magnetic field. Okay? And this is something that I showed here. This fictitious magnetic field is shown by these arrows right here and here. And they have opposite signs because the magnetization decays to the left on one of the edge and it decays to the right on one of the edge. So if you take the curl of it, you are going to have an opposite sign on two edges. So essentially it means that the system shows magnetic field. Now imagine you put in an electron from the left and you want it to pass through this junction. So if this magnetic field is small, it's going to curve the trajectory of this electron in this region a little bit. But when it enters the other edge where there is a magnetic field, okay, it's simply going to straighten out again and it's going to come in. So the conductance is going to be more or less the same. Okay, it's going to be reduced a little bit, but it's going to be more or less the same. However, if the magnetic field is very strong and it's over a small distance d on this edge, the curvature of the trajectory of the semi-classical motion of these Dirac electrons could be so large that they are turned back. Okay? Therefore, the statement is that beyond the critical magnetization, the electrons are not going to pass through this junction. Remember that this happens because of the fictitious magnetic field, and therefore this can happen only with the Dirac electrons on the surface of a topological insulator. This really cannot happen if you have standard Schrödinger electron. Okay? So the statement was that essentially, if you sort of increase the strength of this magnetization, okay, then you will see at some point that these electrons are, they essentially turn back and there is no conductance. And the quantum mechanics of this is very simple. In region 2, when you calculate in the presence of this sigma y term, it is this term out here, in the region, yeah, so in the presence of this sigma y term, if you calculate the wave function of an electron with energy E, epsilon that is, you're going to find that the longitudinal momentum is given by epsilon plus mu, this is the energy divided by h by vf, okay, square, minus ky plus m. Now ky of course is the standard transverse momentum, and m is some effective magnetization that you can find out. Okay. The point is that if you make this m to be very, very large, you see that this kx doesn't have a real solution. Okay, and beyond the critical magnetization of 2 times the energy plus mu, all the ky corresponding to any ky mode, you are going to find that essentially you really do not have any longitudinal momentum which is propagating, which means that you are left only with evanescent modes, which localizes the electron wave function and therefore cuts down the transmission. And that's the physics from a quantum mechanics point of view. From a semi-classical point of view, one can understand this by, looking at the trajectory of these electrons. Okay, and for a strong magnetization, the curvature while passing through this small region is large enough so that it just goes on the other side. Okay. So in either way, the prediction, which was later varied numerically, is that beyond the critical magnetization, the conductance goes to 0. And this, you see, these curves corresponds to, the green corresponds to almost 0 magnetization, the blue a little larger magnetization, and the red is just the critical magnetization. And you see that beyond the critical Z, which is the thickness of this barrier, this magnetization, this just goes to 0. Okay. So this means that you can sort of have a switching device where you can use magnetization as a switch to control electric current. Okay. So therefore, this kind of topological insulator surfaces can lead to very interesting synchronic applications where you can have a magnetic switch which has control over electric current. Okay, is that part clear? Any questions? Okay, if not, let me go to the next topic. Okay, so you can do this with multiple, you can do this with multiple junctions, and you see that this feature remains. Instead of one, you can put many such junctions, and with n equal to 2 and 3, and you find that this feature always remains. Just as for the single junction. But now let me talk about one more thing, or at least two. Okay, so let me see how much time we have. Okay, I think I'm going to cover this Scm spectroscopy, and then if I have time, point out one more thing, but maybe leave that. We'll see. So let's talk about this Scm spectroscopy. Okay. So here, what we are going to do, and this was sort of motivated by Hari Manoharan's work, that we want to find out what the surface of a what the conductance in the or the current on the surface of a topological insulator looks like, provided you inject electrons from an Scm tip to the surface of the topological insulator where there is Dirac. However, instead of a standard Scm out here, you are going to sort of look into a magnetic Scm. That is, the tip is magnetized. It's a ferromagnet. Okay. Now, so let us look into a bit into this, how this thing works. So when you try to calculate this current, what happens is that this current depends on the voltage must be equal to the difference in the energy of the tip and the surface electrons. Okay. And there is a Fermi factor which tells you that both the surface electrons and so there has to be a. So if you are injecting an electron from the tip to the surface electron corresponding to a given eigennumber mu, you have to have an electron occupying the state mu, and you have to have an empty state at mu. Okay, unless this is there, you cannot really inject the electron from the tip to the surface. So there is a Fermi factor which ensures that, and then there is a matrix element. This matrix element essentially tells you the overlap between the wave functions of the tip to that of the topological to that of the wave function on the surface. And this is typically given by the Bardeen tunneling formula, which Bardeen came up with in 1964, where he showed that this just is given by this thing. But the overall thing that I wanted you to take home from this is that it depends on the overlap between the tip and the surface electron wave function. Now consider a standard thing where I have a magnetic sample, which is not a topological insulator. Okay, it's a standard magnetic sample, and let's say that the magnetization of this sample is along a direction theta, so that its wave function for upspin is cos theta by 2, and its wave function for the downspin is sin theta by 2 times some phase. Okay. And this is the non-spin part of the wave function. Okay, and this is the spinor structure. Now the spinor structure of the tip, I'm going to choose my spin quantization axis along the direction of magnetization of the tip, and so it's 1, 0. So now, if I calculate this mu, you see that clearly just by taking the overlap of these two wave functions, that is proportional to cos theta by 2. And since this enters as mu square in the current goes as cos square theta by 2, which is 1 plus cos theta. But cos theta is just the magnetization of the surface. It's just the projection of the surface magnetization on the z-axis. So the current has a standard part and the magnetization. So this is how an Scm tip can be used to sort of measure magnetization of a magnetic surface. Okay? But the thing that I wanted to point out is that there is no dependence in this current on the azimuthal angle of magnetization, which is this, okay, which tells you the distribution of the magnetization in the XY pattern. There is no dependence out here. And the reason there is no dependence is that you always can, and you usually do, fix the spin quantization axis along the magnetization of the tip. So it's always a projection of the surface magnetization on the magnetization of the tip. And that's just the angle difference between the two magnetizations, which is cos theta. Okay? So that's the thing. However, this situation of course changes when you have a topological insulator, because on the topological insulator surface, you have already fixed the spin quantization axis to be perpendicular to that surface. So now the now the tip of the magnetization can have so the tip of the SCM can have a magnetization at a certain angle to this thing, which is given, and therefore its wave function is given by something like this, where kappa nu is some complicated function. And also the wave function of this, the electrons on the surface of the topological insulator is given by this, and the azimuthal angle dependence is given by this beta, okay, or beta mu. And this can also be a complicated function of R and Z. And we are going to take it to be just some constant, but that's just an approximation. However, the point is that now, because your spin quantization axis is no longer determined by the direction of magnetization of the tip, you can have an azimuthal angle dependence in the conductance. Okay? And that azimuthal angle dependence depends on cos of beta minus mu, that is the difference in azimuthal angle distribution of the tip and the sample. Now, I don't want to get into the details of this derivation. However, this can be done pretty easily. But the point is that these topological insulators give you a novel way of determining the direction of magnetization of the electrons in the surface because of this azimuthal angle dependence. And this azimuthal angle dependence is another thing, that if you break the azimuthal symmetry on the surface by putting in an electric field, this electric field essentially parallel to the surface gives you that it changes the tunneling conductance. Okay? So, and that essentially tells you that our electric field which is parallel to the surface and perpendicular to the tip, okay, like here, is going to change the magnetization of or electron propagation from the surface to the tip, which is also very unconventional if you think about it. Normally, this doesn't happen. So essentially, this is another example of unconventional behavior of these electrons on the surface of a topological insulator. Okay, so any questions here? Anything which is unclear? Okay, so then if not, let me just point out one last thing and then I'm going to stop for today. And this would be it for topological insulator, and from the next class onwards, I'm going to talk about Majorana fermions and this mid-gap states in superconductors and those kind of things. Okay, so there is one essential part that we need to understand about this topological Dirac electrons on the surface of a topological insulator. And that is, this topological insulator Dirac electrons has one electron per spin on the surface, whereas a standard metal has two electrons per spin on the surface. So if I try to match the wave functions of an electron on the surface of a topological insulator with that of a metallic film, you normally cannot do it because there is a mismatch of the number of degrees of freedom. Okay. So, however, you can take two of these surfaces of topological insulator and match and sort of couple it to a metallic film which is conventional on the surface of a topological on the surface of an insulator. So these are the surface 1, 2, and 3. But the point is that you do need these two surfaces of topological insulator for being able to connect it to a metallic film like this, or a ferromagnetic. So also here, the other thing to show is that the current continuity that one has, okay, essentially tells you that a current which approaches due to an electron in region 1 essentially gets moved into a current which passes in region 2, which is given by this V2. And remember that the velocity is just V times sigma x for the current along x, because I am taking a sigma dot k kind of dispersion, which means that the velocity along, a sigma cross k kind of dispersion, which means that a current along y out here is proportional to sigma x. The velocity is proportional to sigma x. Okay. And current in the metallic film, which is psi star grad psi. Okay. So this current continuity essentially leads to two linear conditions. One is something similar to continuity of the wave function out here, and the other one is same as continuity of the derivative of the wave function. However, notice that there is always a unknown factor C, which cannot be determined from this effective low energy theory. Okay, this C is expected to be an order 1 number, but it could be anything. And essentially, to determine this, you need to do microscopics, okay, with the full 3D topological insulator. So this is something about the current conduction. And if you use this and you calculate, so you calculate the conductance where you couple a metallic film to these surfaces in region 1 and 2, you find that it gives rise to a spin current. So why does it do that? Remember that when an electron moves in this region 1 and comes and gets scattered from this surface in this interface between region 1, 2, and 3, its direction of motion changes. Okay. As a result, its spin also gets changed, and therefore this kind of scattering essentially is always spin active. Okay, so it distributes the weight of the electron wave function, electron amplitudes in different spin components. And as a result, what passes in this metallic film essentially carries a spin component with it. And what one can show is that there is a Jx or a spin current in response to a applied voltage. So essentially this allows us to generate a finite spin current along X, and also that the magnitude of the spin current can be controlled by an external voltage. So this shows us that the Dirac electrons on the topological and the surface of a topological insulator, because of strong spin orbit coupling, allows us to do many things which are synchronic application. For example, we can switch on or off electric currents using magnetization as a norm, as well as we can apply a voltage and generate spin currents. They're not only charge but also spin currents. Okay? So the take-home message for this is that this would be important in spintronic applications. Okay, if one can manipulate the surfaces properly. Okay, so I think I'm going to stop here and at this point take questions. Okay, I'm just going to put this slide up where we show that we can have this Jx or J0 as a function of the barrier voltage if you put in some barrier, but I'm not going to discuss this very much. Okay, so okay, so any questions? Anything which is unclear? Okay, fine. If not, we are going to stop here today.